My name is Neil Foley. I'm the applications engineer at Rise, and today I'm going to be talking about designing for additive manufacturing versus traditional manufacturing, various methods of producing parts more traditionally. And I'm also going to be talking about the way that, in some cases, after designing a part for traditional manufacturing, there can be issues when converting that design over to be used for additive manufacturing. So we'll start with a quick overview of the different technologies and factors that we'll be looking at. So there's additive manufacturing, also called 3D printing, and this includes a variety of different technologies which we'll look at. There's also subtractive manufacturing. This typically involves using machines to remove material from a stock piece. Then there's molding and casting, which will involve initially producing a molded part and then using that molded part or using the molds repeatedly to produce your end use parts. And then we'll also look at forming, which is a general word to apply to a variety of different technologies that often involve a lot of custom tooling and labor involvement to produce parts using less automated forms of manufacturing. So some of the different things we'll be comparing include the geometric limitations of these different technologies. So oftentimes when designing a part for one type of technology, there are little eccentricities and considerations that will result in a certain type of geometry. And when using that design then for a different type of technology, such as additive, those accommodations can result in poorly produced features and things of that nature. So we'll also look at a few different things, including pre-processing requirements, the amount of work that needs to be done on the front end before a part can start to be produced. We'll also look at material usage versus manufacturing time, which are two factors that can vary in different ways depending on the type of technology that you are using. And finally, we'll look at production volume versus variety, where a high volume would mean that you're producing many copies of the same part, versus a high variety would be if you're producing many distinct versions of a part. And depending on the technology you're using, these two approaches can be more or less appropriate. So first, we'll look generally at additive manufacturing. So a few of the most common technologies in additive manufacturing are filament extrusion, powder bed fusion, and photopolymer curing. So I'll be primarily focusing on filament extrusion, which is the most common type of additive manufacturing and the type that's used by Rise. So there are a few different approaches to pre-processing. Typically, it will involve a model slicing software. There are, in some cases, proprietary softwares, and in others, there are open source softwares that you can use to import a model file and prepare it for the 3D printer to produce the part. And this is typically a pretty quick process. There's a bit of knowledge involved in designing how you want the model to be sliced, but generally it's as simple as importing a file, hitting slice, and sending it over to the printer that you're using. So it's not a very long process to pre-process. It's not very long to pre-process parts for additive manufacturing. Some of the other things to consider are that the production time and cost of additive manufacturing scales approximately linearly with material usage. So if you're producing parts in high volumes, that does not necessarily mean that the parts will be less expensive per part compared to if you produced only a few of that part. So there are not really any benefits to producing parts in high volumes. There are also no additional costs to making changes to the designs that you're using. So if after printing hundreds of copies of one version of a part, you then want to make a slight change and continue producing it, there is no significant overhead there. It will be as simple as bringing the new file into the model slicing software and sending the new version over to the printer. So the first traditional manufacturing method we'll look at is subtractive. So a few of the common forms of subtractive manufacturing include milling, turning, and drilling. So milling is the form shown in this picture here, where you have a sort of drill bit that is rotating and removing material from a stock block to produce the desired shape for the part. Turning would be somewhat similar, but rather than a stationary block, the workpiece would be rotating and material would be removed as it spins. And then drilling would simply be sort of like milling, except the drill bit would only be moving up and down to produce circular geometry and holes. So in terms of pre-processing, subtractive manufacturing can involve somewhat of a range of different amounts of pre-processing. In some cases, if the subtractive manufacturing involves manual operation, which would mean that the person operating the machine would be performing all of the operations by themselves. There would be no automation involved. On the other hand, you can have highly automated subtractive processes where all of the necessary operations are programmed into the manufacturing process and can be performed automatically. So typically, you will have an operator overseeing the process, no matter whether it's manual or pre-programmed, but there is a lot more labor involved in manual performance, and it also tends to take longer than automated production. So one of the major differences between additive and subtractive manufacturing is that whereas additive will be adding material to an empty build plate, subtractive manufacturing typically starts with a material stock that is then milled out and material is then removed. So it's often best to design subtractive manufacturing products to not need a lot of material to be removed. So they'll often be designed to be more bulky. Whereas if you were to mill the type of part that is more designed for 3D printing, you could find that there is a lot of waste material due to the amount that's being removed from the starting block. So because of this relationship, the production rate is not strongly correlated to material usage per part. The production rate is more strongly related to the amount of material that needs to be removed and the amount of complexity in the different geometries of the part. So typically, if you need to make changes to the production of a part, it is not a very expensive operation. You can, if it's manual, just change the way that the operation is done, and if it's CNC programmed, typically you won't have to rewrite the whole program. You'll just have to add a portion to it to accommodate the new design changes. So now I'll be directly comparing some of the best design practices for additive versus subtractive. So one of the things to consider is the part volume and time to add versus time to subtract material. So as I mentioned, additive manufacturing will start with nothing and build the product from an empty build plate, whereas subtractive will start with a stock block and remove material. So because of this, if you have a large volume part, it's often difficult to produce it in a reasonable amount of time using additive manufacturing, whereas that doesn't have much of an effect on subtractive manufacturing. So if you have designed a part for subtractive manufacturing, which has a lot of extra material attached to it, or conforms to the shape of the stock material, then preparing it for additive should probably involve removing some of that excess material and slimming it down to just the necessary portions. So some of the geometric limitations associated with the two processes include feature complexity and organic surfaces. So there is not a lot of limitation on the amount of complexity that you can produce using additive manufacturing, because you are creating a part from an empty plate. You don't have to worry about the limitations of tools that you would be using to remove material. So the types of tools that you're using to remove material with subtractive manufacturing will have certain limiting diameters and other geometric features that prevent them from producing such small features and in such high volumes as you would be able to with additive manufacturing. Another consideration is organic surfaces, which can be produced very easily with additive manufacturing, just as easily, in fact, as flat surfaces, whereas with subtractive manufacturing, organic surfaces can take a long time and a lot of work to make them come out well. So related to that is surface finish considerations. Oftentimes with subtractive manufacturing, you can get a very smooth surface finish without a whole lot of work. However, if you're trying to produce more complex geometry, it can be much more difficult to get a good surface finish, such as on those organic surfaces that I mentioned. Now with additive, it's in some cases, depending on the technology, also fairly easy to get a good surface finish, but there are also some special cases, such as very shallow surfaces, shallow meaning surfaces that are close to horizontal but not quite horizontal, and surfaces like these can produce somewhat stepped surface finishes that are not as smooth as you would get with a subtractive type of process. So in some cases, it's better to redesign the way your surface is laid out in order to get the surface finish that you're looking for. A few other things to consider are undercuts and concavity. So the undercuts are fairly easy to produce with additive manufacturing. They'll often require support material, which can then be removed in different ways. One of the capabilities that subtractive manufacturing now has is there are 5-axis milling machines, which are quite expensive and complex, but they can produce very complex geometry, including undercuts and concavity. But more traditional milling machines will be unable to produce this type of geometry unless the process goes through multiple steps of rotating the part. Another consideration is the size of the part. So large parts are often more difficult to produce with additive manufacturing. It's better to focus on just the vital geometry rather than making things bulkier. However, it's also possible to combine additive produced parts together using gluing or fastening, in some cases in the same way as you would be able to with subtractive. And then a final geometric limitation is sharp corners, and the corners of parts when produced with additive, depending on whether that corner is convex or concave, will determine how sharp it can be produced. So concave corners can be essentially as sharp as needed, whereas convex corners are limited by the width of the nozzle that is extruding material, and also by the material properties of the material that's being used. On the other hand, subtractive manufacturing has sort of an opposite situation where the convex corners can be as sharp as desired, and the concave corners have a limited radius based on the radius of the milling tool that's being used. So if a part has been designed to have corners that were developed for subtractive manufacturing, and that part is intended to be prepared for additive manufacturing, it can be good to go through and look at those corners and make sure that all of the convex ones and concave ones are prepared properly for the process you're using. A final point I have here is anticipating post-processing requirements, and this is related to the fact that after producing a part with additive manufacturing, there will often be a support removal step required, and in some cases, some other post-processing steps, whereas with subtractive, you can often take the part right out and use it immediately, although in some cases there will be polishing and other post-processing steps desired. So one of the things that you'll want to do when designing for additive is anticipate the type of post-processing required, such as where supports will be and how difficult it will be to remove supports, and consider how you can design the part to avoid any difficult or lengthy post-processing. So now we'll move on to another type of manufacturing. So this is molding and casting, which includes a variety of different technologies. I have a few major ones here. Those are thermoplastic injection molding, die casting, which is similar but done with molten metal rather than thermoplastic, and also investment casting, which is sort of a combination of a few different molding technologies. So in terms of pre-processing, there is typically an initial step of designing and then programming the machining of the molds that you're going to be using. So this will be at least as complex as designing the production of parts for subtractive manufacturing, and those molds will then be produced with subtractive manufacturing, but they typically require a very high quality compared to other parts that you would produce. Now, once that mold is completed, you can then start using it to produce parts very rapidly, and each mold that you create will be able to run its own channel of producing parts. And also, if you really need a lot of volume, then you can even make a mold that is capable of producing multiple parts at once. And this gives you the ability to scale your production even further using parallel production. Now, despite the ability of this approach to produce parts at very high scales, it's also very expensive to make any design changes, because if even a minor change is made to the end use design of the part, then you'll need to go all the way back to the beginning and design, program, and produce the expensive molds. So now we'll look at a comparison of additive versus molding, some of the design practices that are good to consider. So in terms of geometric limitations, one of those things is fine features. So I mentioned that depending on the technology you can use, you can get very fine features with additive manufacturing. However, there are typically limitations on that fact, especially depending on the orientation that the features are produced in. So molding thermoplastics can typically allow you to produce very narrow walls and very fine features, and it's able to do this because it doesn't have any limitations on the width of a nozzle or things like that. It's injecting the plastic directly into the mold cavity and filling it out any space that's inside. However, there are some things that you'll want to be careful of if a part has been produced for molding and that is to make sure that any fine features or thin walls that have been designed when transferred over to additive manufacturing will not be incapable of being produced. There are cases where a very fine molding part has been molding part design has been ported over to additive manufacturing, and some of the features were too narrow to be even produced by the nozzle. So a few of the other things that are often used in molding include bosses and draft angles. So drafting is required to allow a molded part to be removed from the mold so that it doesn't get trapped inside after cooling. And this type of feature is not required for additive manufacturing technologies. So if a part has this type of feature, then it's often better to just ignore or remove it once you port it over to an additive technology. A few of the other things, as I mentioned, include undercuts and the complexity of the mold assembly. So while molding parts does allow you to produce undercuts in the same way as additive manufacturing can produce undercuts, typically using undercuts with a molding design can significantly increase the complexity of the mold assembly. This is because each undercut that you include will likely need a separate component to a separate moving component that can be added and removed from the mold in order for you to assemble it together and then not get the part stuck inside after it finishes cooling. Some of the other design features that I often see for parts that were designed for molding include gates, runners, and ribs. And some things to consider with these when using them for molding include the difficulty of filling them, because if a portion of a mold geometry is too narrow, then it's possible that the molten plastic will not be able to enter into it, and you'll end up with a void or empty space in the part. With additive manufacturing, it's of course better to just remove the gates and runners, which are the connections between different parts in a mold. But with regard to ribs, the main thing you'll have to be concerned with is just making sure that they're wide enough to be produced by the additive technology that you're using. And finally, one of the things that's sort of opposite compared to the comparison with subtractive manufacturing is that molding part design usually avoids bulky features. It's better not to have any regions that have a lot of material, because this can take a lot longer to cool and have the part ready, and it can also cause some deformation as the part is cooling. So if this is the case with a part that you're looking at that's been designed for molding, then in some cases it may in fact be better to add material to strengthen the part, because with additive manufacturing you won't have to worry as much about that sort of deformation as the thermoplastic cools. So a final thing to look at is the fact that, as I mentioned, when redesigning a part for molding, it will often be very expensive because you'll have to go right back to the beginning of the process and create a new mold. But there is a special case where, when redesigning a part that is only adding material to the prior design, it's sometimes possible to continue using the same mold and just to machine out the additional region that needs to be filled. And in this way, it can be much cheaper than if you were to be removing material, which would require you to go all the way back to the first step. Now, finally, we'll look at forming. So this is including a whole variety of different approaches to manufacturing. I have a few listed here, including forging, pressing, and different approaches to preparing sheet metal, including stamping and bending. And I'll be primarily focusing on sheet metal because this is type of part that has often been ported over to be produced with 3D printing. So in terms of pre-processing, oftentimes when designing processes to produce parts for forming, there will be custom tooling required and also some amount of expertise required to design the process to produce the part. So this can involve much higher labor costs due to the expertise required to design the process, as well as the attention required to carry out the process. Now, oftentimes producing a small number of parts using forming will require direct attention on the part at all times as it's being produced. But in some cases, costs of these parts can be reduced for high volume production by automating the process with robots or certain stages that can be applied using automated machinery. Also, minor design changes can often be integrated at relatively low additional costs for forming, because either the operator who is performing the operations manually will simply be able to integrate the new design changes, or the processes that are being used can just be switched out without a whole lot of overhead involved. In some cases, there will need to be new custom tooling developed, and that can increase the price more. So now to compare best design practices for additive versus forming, we'll look at a few of the geometric limitations. These include the feature complexity and labor cost involved in forming. So as I mentioned, additive can have fairly fine features and a lot of geometric complexity with no additional cost compared to geometric simplicity. But if you want to produce complex features or complex geometry using forming technologies, it can be very labor intensive with many separate steps, and that can be quite costly. So oftentimes parts that are designed for forming will have very simple geometry, and simple is often good, but can in some cases be inefficient or non-optimal. So if a part has been designed for forming and is now being ported over to be produced using additive manufacturing, it may be worth looking at whether a bit of additional complexity will improve the function of the part, since that complexity will not increase the cost or time required to produce the part. So also regarding sheet metal produced using a flat pattern has a few specific limitations. One of those is the way that once the sheet metal has been folded into shape, there will typically be gaps at the edges that are meant to meet, and those gaps can be filled with welding, and that's fine. That is one additional post-processing step that should be considered. There's also the fact that producing sheet metal parts from flat patterning will involve a constant sheet thickness, so you won't be able to produce parts with variations in the strength so that you can strengthen one portion without needing to thicken the rest of the part. And there are some exceptions to these things if you use special machinery for them. Finally, it's very difficult to produce anything but zero curvature products without special equipment. So zero curvature would be if you start with a flat sheet and then curve it along some radius. You won't be able to then curve it along a perpendicular radius in the same region. You won't be able to produce sphere-like objects or saddle-like objects without equipment that's been specifically designed to produce those things, and that can be an expensive process. So all of these things that I've mentioned regarding producing sheet metal parts from flat patterns are not really relevant to producing parts with additive manufacturing. You don't have to worry about the curvature of surfaces or the limitations on thickness. You can have any variation in the curvature or the thickness, and you can, of course, avoid meeting avoid any gaps at meeting edges just by designing them not to be gaps. So now I'll just quickly go over some of the special capabilities of additive manufacturing. Now, there are a lot of things that additive does very well and even better than other technologies, but this is just going to focus on things that additive does exclusively. And these are some things to consider taking advantage of when taking parts that have been designed for other technologies and then moving them over to additive. Being able to apply some of these changes can, in some cases, improve the cost or speed of a process, or even the function of the process quite a bit. So one of these is consolidating assembly components. So this would be applicable to cases where the complexity of a design requires that it be produced in multiple pieces if it's to be produced using traditional manufacturing methods. So in the case of additive manufacturing, because there are fewer limitations on the complexity of geometry, it's often possible to take these multiple assembly components and combine them into a single part that is printed all at once. And this can save quite a bit of the complexity of assembling and fastening components after production. Another thing to consider is that additive manufacturing can produce parts with internal cavities, which can't be done with many other manufacturing technologies. And also using a sparse fill, it's able to accelerate its production and conserve material, whereas any other production manufacturing technology is going to be solid all the way through and use material to fill out any of its volume. Another capability of additive is that because it builds one layer at a time, it's able to embed inks, fibers, and other technologies into its volume. And in some cases, it's also capable of using multi-materials to combine different material properties into a single part. And finally, additive manufacturing allows you to harness fully organic generative design, or topology optimization, which allows you to optimize the design of your part to accommodate different specific physical requirements. And this typically produces very complex organic geometries like that shown in the image here. And while this type of part would be very difficult to produce using any of the other technologies discussed here, it's quite simple to produce it using additive manufacturing. So that's quite a useful capability. So that's all I have for today's webinar. I'm going to stick around for a few minutes to answer any questions that anyone may have. If you do have questions, you can type them into the chat box and I'll answer them as they come. Other than that, thank you all for joining us for today's webinar and have a nice day.